This video is part of the MCAT chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to go over reduction and oxidation and how to recognize that based off of structural changes and based off of oxidation numbers. Reduction is a term used whenever an atom gains electrons, and oxidation is the term whenever an atom loses electrons. In our first example, we are showing the transfer of an electron from a sodium atom to the chlorine atom. So the sodium was oxidized and the chlorine was reduced. And anytime something becomes oxidized, so the sodium became oxidized because it lost an electron, that means that it had to reduce something else because it gave up the electron to another atom. So that makes the sodium what we call a reducing agent. And then conversely, the chlorine accepted an electron, which means that it took an electron from something else, so it oxidized another atom, which makes the chlorine an oxidizing agent. So the first example is a really straightforward one where we have the transfer of a full electron. The second example is where we see a change in electron density, so we don't see an entire transfer of an electron like we see in the ion formation of sodium and chloride. For the second example, the electron density for an atom increases for the atom that gets reduced, and then the electron density decreases for the atoms that get oxidized. So for the second example, let's look at the carbons. And we are trying to determine which carbon is the most reduced or the most oxidized. In this arrow here, that's not a reaction arrow, so we're not changing the first structure into that second structure. We're just comparing the carbons in the two structures to talk about which one is more reduced or oxidized. In the first molecule, the carbons are attached to two hydrogens and one carbon. So they're each attached to two hydrogens and one carbon. Whenever you're trying to determine which one of these has more electron density, therefore which one is more reduced, all that you want to think about is electronegativity. So determine what's the electronegativity of the atom of interest. So the atom of interest is carbon. And then what's the electronegativity of the atoms that it's attached to, which would be the hydrogens and then the other carbon. So the electronegativity of carbon is higher than hydrogen, so it's pulling some electron density away from hydrogen. And if you're thinking right now that that's not a polar bond, you're correct, it's not a polar bond, but carbon is a little bit more electronegative than hydrogen, so it does pull some electron density from it, but it's definitely not a polar bond. And then the carbon-carbon bond, neither one of those carbons is pulling electron density towards itself from the other one because their electron densities are the same. So for the structure on the left, our carbons are pulling electrons from the hydrogens, but not from the adjacent carbons that they're attached to. And then if we look at the one on the right, this carbon is attached to four hydrogens. So just for the same reason we discussed before, it's able to pull some, not a whole lot, but some electron density from all four hydrogens. So the carbon on the right has a higher electron density than the two carbons on the left because it's attached to four hydrogens, where the ones on the left are only attached to two, which makes the one on the right more reduced compared to the one on the left. And again, this is not a reaction going from the structure on the left to the right. We are just comparing the two molecules. Now we'll look at how you recognize reduction and oxidation based off of structural changes. And on the MCAT, there's a few different ways in which they're going to test you on recognizing oxidation and reduction, and one of these will be by analyzing structural changes. And a reduction will happen whenever you notice that an atom has become attached to a less electronegative atom throughout the course of a reaction. And then conversely, oxidation will lead to an atom becoming attached to a more electronegative atom. So we have two examples here to illustrate what happens with those two situations. The most common way that they test on reduction is through the addition of a hydride ion to a molecule. And what this hydride ion does is it acts as a super strong nucleophile because hydrogens are not used to having that lone pair on them. So whenever it has that lone pair, it really wants to react. So that lone pair is going to attack. Usually it's going to be a carbon, but sometimes it could be other things. You don't need to really memorize at all this mechanism, but just to help you with understanding it, when it attacks that carbon, this double bond will break and then it will go grab a hydrogen that's in solution, because remember, no matter what the solution is, even at pH 7, there are some hydrogens that are floating around in solution. And then that's going to lead to a structure where each carbon now has three hydrogens attached. So from the perspective of these two hydrogens, we want to think about their attachments to more or less electronegative atoms throughout the course of that reaction. So in the beginning, it's just like the molecule we talked about at the beginning of this video. So they're attached to the 2 hydrogens and then 1 carbon, which is just each other. And then after the reaction, they are both attached to 3 hydrogens. So throughout the course of the reaction, they became attached to more less electronegative atoms than they were attached to in the beginning, which that is the telltale sign for whenever something gets reduced. And in general, it's pretty safe bet that whenever something gets reduced, you're going to see more bonds to hydrogen, and it is through this hydride ion reaction that happens. In the next example, we're going to look at something getting oxidized. So our molecule on the left, this carbon is attached to 3 hydrogens and then 1 oxygen. This symbol here is just to show that oxidation is occurring. And if you know a lot about oxidation, you may be thinking that we should turn this into a carboxylic acid. We're just going to look at if we oxidized it one step. So we are just turning this into a ketone. So by oxidizing this, we're increasing the number of bonds to that oxygen. So our carbon went from 3 bonds to hydrogens and 1 bond to oxygen. And now we only have 2 hydrogens. So there are 2 bonds to hydrogens. And now there are 2 bonds to that oxygen. So we have 2 bonds to oxygen. And that oxygen is pulling electron density away from the carbon. So the carbon now, through the course of the reaction, has lost electron density. And one of the main ways you can recognize oxidation is that you will often have more bonds to oxygen, hence the name oxidation. The second most common way they're going to test you on recognizing oxidation is with oxidation numbers. And this is usually whenever you're not given the structure of a molecule and they just give you a reaction with the molecular formulas. And whenever they ask about redox reactions and they have molecular formulas, look for oxidation numbers. Oxidation numbers are just numbers that are used to represent how reduced or oxidized an atom is. A lower number indicates that we are more reduced, so we have more electrons, and a higher number means that we are more oxidized. And a lot of times these are going to be negative numbers. So if you have a super negative number, that means that you have a lot of electrons. If you have a really positive number, that means that you don't have a lot of electrons or your atom has really low electron density. And these numbers are assigned by following this list of rules. Something that's important about this list of rules, which is listed right here, is that these have to be followed in order. So these rules have what we would just call priority. Now let's just practice assigning some oxidation numbers to these different molecules. For the first rule, the oxidation number of all the atoms are going to have to add up to the charge. And for H2O, there's no charge written, which means that it has a charge of 0. So our oxidation numbers will have to add up to 0. So for oxygen, rule number 2 says that this oxygen is going to get a -2, and there's no rule with a higher priority that would make that one not true. So now, notice that rule 5 does tell us what to do with hydrogen, but it doesn't even matter because we know oxygen has to be number 2 because it's a really high priority rule, and the oxidation numbers have to add up to 0. So that means that our hydrogen atoms are going to have to offset that -2 to get us to 0. So hydrogen will be +1 because there are 2 hydrogens. So total, the 2 hydrogens will give us a total of +2, which will offset the oxygen's -2 and give us a total of 0. And I strongly recommend that whenever you're writing oxidation numbers, don't write the total that all the atoms are going to add up to give you. Write the oxidation number for each atom. So we have 2 hydrogens here. Each one is +1. So write the +1. They add up to +2. Do not write the +2 or else it's going to get really confusing whenever you're tracking changes to oxidation number. If you want to put it in parentheses like I did there, that'll be totally fine. But always make sure you put the +1 to signify what the oxidation number is for each hydrogen. Moving on to number 2. Again, we have a 0 charge, so all the oxidation numbers need to add up to 0. The next rule is oxygen, so we know oxygen will have a -2. Now we have phosphorus, and we look at our rules, and none of our rules really apply to phosphorus. So the only rule that tells us what to do would be that first one, in that our oxidation numbers are going to need to add up to 0. We have -2 for each oxygen, so total we have -10. We have 2 phosphorus molecules, so that means that they're going to have to offset that -10, which gives us an oxidation number of +5 for each phosphorus, or +10 total for the 2 phosphorus atoms combined. For number 3, we're at 0 again. Our first rule that gets applied is -2 for that oxygen. Now go through your list. of your oxidation rules and see what applies. Numbers 3 and 4 don't apply, but now we hit number 5 and we see that we do have hydrogen, so that is a +1. So total right now we have +12 from hydrogen and -2 from that oxygen. So we are at a total of +10. And we need our carbons to offset that, so that way we are still following rule 1. So for 5 carbons to offset +10, each one would have to be -2.